we learning about the ideal gas law. The ideal gas law relates the pressure, volume, number of moles, and temperature of a gas. Thus far, we have been working with simple gas laws that only contain two variables, such as Boyle's law, which shows that pressure and volume are inversely related when the number of moles and temperature are held constant, or Charles' law, which shows that volume and temperature are directly related when the number of moles and pressure is held constant. This week, our lab introduced us to Avogadro's law, which shows that volume and the number of moles are directly related when pressure and temperature is held constant. When we combined Boyle's law and Charles' law, we came up with the combined gas law, which was P1 times V1 over T1 equals P2 times V2 over T2. You can see that we have introduced a new variable with Avogadro's law, that variable being N, which represents the number of moles. If we add that variable to our combined gas law, we now have P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. Oftentimes in a gas, we must include more than two variables, so we will be using what's called the ideal gas law. To simplify this equation, we are going to take one side of it and set it equal to standard conditions. We have learned that Avogadro's law says at STP, 1 mole of any gas takes up 22.4 liters. Remember, STP stands for standard temperature and pressure. Oftentimes, volumes of gases are compared at STP, since volume of gases change with pressure and temperature changes. So I am simply going to take the information that I have here, and we are going to plug it into this portion of the equation so that we have one side of the equation set to standard conditions. So standard pressure is 1 atmosphere. Volume is 22.4 liters. Volume of 22.4 liters is when we have 1 mole of gas. And our temperature is 273 kelvins. If we multiply that out, we get 0.08205. Notice that if you're looking at the information I use, that there are 3 significant digits in every single variable in this equation. So I am going to round this number to 0.0821. As far as units go, notice that none of our units in this equation cancel out. So I must keep atmospheres, liters, moles, and kelvins. This number has a special name, and it is called the ideal gas law constant. And we give it the variable letter R. So if you can see here, we now have R equals PV over NT. Generally, this is not how you will see this equation written. It will not be solved for R, such as I have just done here. It will be written in the form PV equals nRT, which is the ideal gas law. So let's break the ideal gas law down a little bit. P is pressure measured in atmospheres, V is volume measured in liters, N is moles of gas present, R is a constant that converts the units. Its value is 0.0821 atmospheres times liters divided by moles times kelvins. T is temperature measured in kelvins. Just to review, it is important that the pressure, volume, number of moles, and temperature are in the specific units because we need those units to cancel with the units in R. And number 6, simple algebra can be used to solve for any of these values. So you can see that the equation has been solved for all 5 variables. Let's try an example. Our first problem here, our first and only, yay! What volume would 20 grams of ammonia gas occupy at 750 millimeters of mercury and 30 degrees Celsius? Well, I know that I am probably going to be using the equation PV equals nRT. And it is telling me that I am going to be solving for volume. So if I divide both sides of the equation by P, I am going to be solving for volume, and volume is going to equal nRT divided by P. So I need the number of moles. Well, if I'm reading through the equation, I notice I am given a mass, and mass can be converted to moles. So I'm going to take 20.0 grams, and the gas is NH3, so 20 grams of NH3. I know that NH3 has one nitrogen, which has a molar mass of 14, has 3 hydrogens. Each hydrogen has a molar mass of 1. So the molar mass of the compound NH3 is 17 grams per mole. So in this particular case, I know that 17 grams is 1 mole of gas. 20 grams has 3 significant digits, so I will keep my moles to 1.18 moles. I can now substitute that into my equation. The next variable that I'm going to need is R. So in that particular case, I'm going to put it 0.0821 liters times atmospheres over mole times Kelvin. Remember, that's a constant. Whenever you see R, you will be using this number with those units. T, I'm giving a temperature of 30 degrees Celsius. However, just like in all of our gas laws, we cannot use the temperature in Celsius. We must convert it to the Kelvin scale. So if we add 273, we have a Kelvin temperature of 303 kelvins. Our final variable is pressure. Notice that our given pressure is in millimeters of mercury, but our ideal gas law constant's pressure is in atmospheres. So once again, we must convert our unit to the proper unit. There are 760 millimeters of mercury in 1 atmosphere. So 750 divided by 760 is 0.987 ATMs. Again, I'm keeping 3 significant digits because the 750 with the decimal at the end would be 3 significant digits. That value then will go on the bottom of my equation, which is 0.987. I will then use a calculator and I will multiply 1.18 times 0.0821 times 303 divided by 0.987. Significant digits wise, the 1.18 has 3, the 303 has 3, the 0.987 also has 3. The ideal gas law constant will never ever be used to determine your number of significant digits because it is a constant. So the final answer to this problem, the 3 significant digits, is 29.7 liters. And what kind of gas do we have? We have liters of NH3. That's a wrap.